Alrighty. All right. So today I wanted to look at difference between two squares. I'd mentioned this to you before, but you notice for the very first time that I've actually made some notes on some things that we've done to this point because it's important for us to follow through and to build on what we've done. So the very first thing that I mentioned here is that we have notes on factorization, but these notes are referring to factorization by grouping as our base. And we know that when we factorize by grouping, we need to have four terms, right? Not only that, we need the terms in the middle of the four, right, to share factors with the terms on the end. That allows us, doesn't matter which way we switch things around, to be able to factorize by grouping and end up with that very neat binomial product or product of two binomial terms, right? No, when we got to quadratic factorization, that was a little bit different because we had three terms, right? We have the quadratic form, which is the ax squared plus bx plus c. So I had three terms, and our job was to convert or rewrite those three terms as four terms so we could get back to factorizing by grouping. But with a difference between two squares, you have two terms, right? And the example we're going to start with is x squared minus 9. And the question again is, if we've been factorizing by grouping, and with quadratic factorization, we move from three to four terms. When we start with two terms, as is the case here, what are we doing? Right? So let's take a look at the process. I'll start by just talking about a difference between two squares quite literally as an expression, and why it's called what it's called. And that's very quick. And then we'll talk about what we need to do. So if I said to you, have x squared minus 9, the difference comes from the operation in the middle, right? We have a subtraction here, and so we're finding a difference between two terms. But more specifically, those two terms are x all squared, and in this case, we could look at this 9 as 3 all squared. So quite literally, once we can identify that we have two squares and there's a difference between them and there's a subtraction, another way of saying that, then we literally have quite literally a difference between two squares. Now, the question is, what are we going to do? Now, we're going to be able to at some point, not too far off from here, be able to move from this to our answer immediately, right? Once you've identified the squares, you have the factorization. But I want to take it back to and connect it to what we did with factorization by grouping. What if we move from two terms to first three terms? And I said to you that term in the middle is 0x because I don't have to write 0x. 0 times anything is 0, which would explain why we can just say x squared minus 9. And if I consider this to be 0x, then we have three terms. We have that quadratic form, that ax squared plus bx plus c that you're accustomed to. And we can do what we've been doing, what we did with quadratic factorization, which is to convert this to a four-term expression. All right? My boxes are immaculate. Anyway, yeah, so these two terms in the middle must sum to 0x, but must be factors of both x squared and negative 9. That's the process, people. So we know what we did before. We multiply that first by that last term. And in this instance, we get negative 9x squared, and we need the factors of negative 9x squared that sum to 0. Now, because it's negative, it's always going to be negative. It's a difference between two squares, right? Then we know that to get a negative as a product, you need to have a positive factor and a negative factor. One of the terms has to be positive, one has to be negative. And in this case, they both have to be equal. And you know the factors of 9, and immediately you should be able to say, oh, I can use 3x, and I can use minus or negative 3x, right? So I could rewrite this as x squared minus 3x plus 3x minus 9. And you wouldn't have an issue because you're now familiar with this, and now we have our four terms, and now we can factorize by grouping as we're accustomed to. Now, does it matter which goes first? No. Plus 3x minus 3x doesn't make a difference. And so we can factor here, and what's common between these two terms is going to be x. What's left here is x minus 3. And as you know from what we've been doing, whatever I get in this bracket, I want it back in this bracket. And I can say to myself, what times x then gives me 3x, and that's positive 3. and 3 times negative 3 also gives me negative 9. So we're in good stead. All right, we're kosher. Everything is working as expected. So let me leave that right there. And so we end up with now, when we factor out x minus 3, it's just going to be x minus 3 times x plus 3. All right. Now, effectively, what you will be told is that, hey, you could have gotten that at the beginning because you had x squared minus 9 squared, and this is really x all squared minus 3 all squared, or in brackets squared, 3 squared. And I could move from this step, once I've acknowledged that I know what the squares are, to saying that my solution is going to be x plus 3 times x minus 3. Now, the point is not to say that you're going to have to go through the entire process that I just went through. The idea is that I need for you to understand that this connects to what we did before with factorization by grouping. No one expects you to go back through this process. It's now going to be all about identifying the squares. So if I say to you, cool, this is straightforward for you, right? What if I have, here's a question. What if I have x squared minus 25, right? Can I identify squares? You'll say, definitely, this is light work. My squares are x and 5. These are the terms that are being squared, which means the factorization, therefore, is going to be x minus 5 times x plus 5. That is the expectation. As a matter of fact, this middle line is not even necessary, right? But it's all about comfort. And so I need for you to be able to identify the squares first, because it's going to be harder for you to make a mistake if you identify squares. And my thing is, you can always jump from here to here. However, if you do make a simple mistake, it's always good to have a line that explains that you know between the first line and the answer that you are moving in the right direction and you had an idea of what you're doing and what was made. Any error in the end would have been, simple calculation or miscalculation, right? You would have gotten maybe a consideration or a point for going in the right direction. In math, the answer is a mark. Process gives you marks as well, so keep that in mind. All right, let's try again. All right, it becomes pretty straightforward. So I could go m squared minus 49, and you'd say to me, all right, more of the same. And so we end up with m minus 7, m plus 7. Now, there isn't much more we can do with this, right? The only thing that we can do is to, write questions a little bit differently to see if you acknowledge and recognize what it is that you're looking at. So there are a couple. Let me try another question. Let's add a page if I can. All right, so let's get to this page. All right, so I do have a couple of questions that we can look at, and I'll try to find some that are semi-decent. What if I had, let's go, 1 minus m plus n all squared, right? That's still a difference between two squares, people, right? The only thing that I've done here is to use the term 1. And if you can acknowledge that 1 times 1 is 1, then I can express 1 as 1 squared. And then my squares are going to be as follows. And then my solution is going to be 1 minus all of this times 1 plus all of this, right? And you can simplify this, becomes 1 minus m minus n, because the negative multiplies what is in the bracket. It's distributed, this negative 1 is distributed across the m and the n. And what you have over here is 1 plus m plus n, right? That one looked a little bit different, but it was the same premise, right? Same principle. What else can we do? It's not. It's pretty much it. What if I gave you something that looked like this? Let's go 100 a squared minus 81 b squared, right? Again, just identify the squares. The first square could be 10a all squared, and the second square could be 9b. all squared. And once I have the squares, then my factorization becomes 10a minus 9b times 10a plus 9b. Does it matter which of these we put first? Nope. We know in practice that multiplication is commutative. And so some people say commutative, whatever. Tomato, tomato, right? The point is the order of the multiplication makes no difference. 3 times 2 is the same thing as 2 times 3. Both are 6. So we're comfortable there. All right, let's try something that looks a little bit different. Let's try another one. I'll try to give you as many flavors of this thing as I can find. All right, let's try 4x squared minus y squared over 4. Prettiest y you've ever seen in your life. I know, but say less. What are the squares? Again, 2x all squared minus y over 2 all squared. You should be comfortable, right? You could have done a separate step if you wanted to. You could have looked at this as 2 squared x squared minus y squared over 2 squared. I don't know if that would make it easier for you to identify the squares. And then you could put the squares over here all in one bracket and the squares over here all in one bracket, right? And so we end up here, and that means that our factorization is simply this square minus this square times the first square plus the second square. And that's it, right? Doesn't get too technical there. So we won't belabor the point. I think you should be fairly comfortable. And what I'll do, as I've been doing recently, is to kind of put a worksheet out there so you can practice. Hopefully, I'll put some challenging questions in that if I can find any. I'll do one other of the fractional type, and then I'll try one that I think might be a bit more challenging. It's a proof. So let's go a squared over 25 minus b squared over 16. Now we can identify the squares if you please. A squared over 5 squared minus b squared over 4 squared. And that means our squares are effectively, wow, a over 5 all squared minus, this is a b, promise, over 4 all squared. And so our factorization, let me put this up here, is a over 5 minus b over 4 times a over 5 plus b over 4. And we're good to go. That's that. Now, I did come across an exam question I thought was pretty interesting. So I said, let me try to bring that to you. Just show you that maybe some questions can be written in a way that's a little bit different to what you anticipate. The point is to recognize a difference between two squares, right? So here we have x plus y plus z. That's a z or a z depending on how you set it. All squared minus x plus y all squared. And we need to show that, wow, that's what that's saying. Show that this is the same thing as 2 open bracket x plus y z plus z squared. I have not worked this out. We're just going to go. Where are we going to go and see how this works? But we recognize that this is a difference between two squares. We have the squares in front of us. So this line, if we're trying to prove it, if this is a square and this is a square, should be the same thing as this, right? Minus this. Do I have space? Times the first term plus the second term. I'm squeezing everything in. All right, kind of fit. Not so much, but it was close. Let's start over here. So when we're looking at this major bracket, we can just rewrite everything here. And I'm subtracting from it these two. All right, and here we're just adding everything. What does that leave us with? Well, this leaves us with x and minus x canceling, y and minus y canceling. So we end up with z times what looks like two x's, two y's, and one z. So what were we meant to prove here? Well, okay, that is interesting. So we can expand it. Let's expand it a little bit because we're meant to prove this here, right? We're meant to prove or get that in the end. So let's expand what we have. I'm going to shift this up a little bit so we can do that. Can I keep that in view? I can possibly. So I'll expand and I might just use over here as well. So when we expand, we get 2xz, we get 2yz, and then we get z squared. And these two terms here, I've reduced the amount of space I have ridiculously with this arrow, but I can factor 2z out of this, right? Is that what they did? They did, and then they had x plus y, and that left us with z squared. The only thing that they did differently is that they put the z on the right hand side and the 2 on the left hand side of the bracket. But multiplication is commutative, so this does equal 2 times x plus y z plus z squared. This is a z, all right? Today it's a z. It works for us. And again, us saying multiplication is commutative is saying that it doesn't matter what order you're multiplying. So me multiplying by 2z first, or me multiplying by 2, then the bracket, and then z, it's the same thing. So we were able to prove that, and we're just using a difference between two squares to evaluate this, right? So, gentle people, the process isn't difficult. Hopefully, you understand it. What I'll try to do, like I said, is give you some more challenging questions in the worksheet. And if you have any questions, let me know. Do not forget to like and subscribe. This motivation to get this going and keep it going. And I'm the kind of person that needs that motivation. So sending this your way and see you in the next one.